Analysis of cold plasma injection on Whistler mode instability with AC field in magnetosphere of Saturn. Abstract whistlers generated by lightning have been observed in the magnetosphere of Saturn by the Cassini Radio and Plasma Wave Science Investigation, RPWS. 2 whistlers were observed as the spacecraft flew over the rings on July 1, 2004, and the third was observed on October 28, 2004, during the inbound pass of orbit at a radial distance of 6.18 Rs, Saturn radii. The effect of cold plasma injection on Whistler mode instability has been studied for ring distribution function with perpendicular AC electric field. The dispersion relation of the parallel propagating electromagnetic Whistler mode wave has been applied to the magnetosphere of Saturn. An expression for the growth rate of a system with added cold plasma injection has been calculated. The effects of electron density, number density, temperature anisotropy, AC frequency, and relativistic factor on the growth rate of Whistler mode emission were investigated. The observation is in very good agreement with the results. Analysis shows that an increase in temperature anisotropy, AC frequency, and energy density increases the rate of increase in Whistler waves with significant changes in wave numbers. It has been shown that Whistler mode waves have increased due to the loss of vertical kinetic energy of the ring electrons. In Saturn's magnetosphere, calculations were made at a radial distance of Rs. This result is important for the analysis of VLF emissions observed over a broad spectrum of frequencies in the Saturn magnetosphere. Keywords: Whistler mode instability, ring distribution function, dispersion relation, cold injection. Introduction. Whistler is an audio frequency electromagnetic wave generated by lightning, which propagates along the magnetic field lines at a frequency lower than the electron cyclotron frequency and the electron plasma frequency. Whistling was first discovered in 1918 by one using a basic vacuum tube audio amplifier. Later, two found that the arrival time is inversely proportional to the square root of the frequency. 3 was the first person to correctly explain the origin of Whistler blowing. He showed that the Whistler travels along the magnetic field lines from one hemisphere to the other, and this plasma propagation mode is now called the Whistler mode. Whistlers have also been found on Jupiter 4-7. There are 2 common types of Whistler mode emissions in the planet's magnetosphere, His and chorus. The frequency of the Whistler mode emission is less than the lower of the plasma frequency Fp or the cyclotron frequency Fc. At Saturn, the His usually has an uncharacteristic spectrum, and its frequency is usually lower than the frequency of the Whistler chorus, F3 kHz. It is known that the latter has a source region near the magnetic equator, usually a narrowband structure, and shows many fine structures of drifting frequency tones or at high resolution, which is larger than the typical spectral density. For a long time, people have been well aware of the developed linear theory of chorus generation 8-10. The fine structure of the chorus is the result of electronic nonlinearity and resonance wave capture, as described by 11-16. Diffusion pitch angle scattering and electron acceleration occur on Earth due to Whistler emission 17-19, and may also occur at Saturn 20-21. Recently, it has been demonstrated on Saturn that the same general process of pitch angle scattering by Z mode is important 22. On the Earth, whistlers near the electromagnetic equator will have cyclotron resonance and wave growth 23-24. Earlier theories also believed that whistlers would be generated in the plasma layer 25-27. The long duration of the Cassini mission has given us a deeper understanding of Saturn's plasma conditions and wave characteristics. The ratio of plasma frequency to gyro frequency, FPE/FCE, is very important for electron acceleration generated by wave-particle interaction, and a value of FPE/FCE 4 will result in good electron acceleration 28. The region of interest here is 6.18 Rs. It is reasonable to assume that the magnetic field is a dipole magnetic field near Saturn, which is very small 29. Voyager 1's encounter with Saturn in November 1980 provided the first opportunity to study plasma wave interactions in Saturn's magnetosphere. Inspired by various pioneers, in this work, we try to study the Whistler mode. Instability in the inner magnetosphere of Saturn at a radial. Conclusion. In this work, Whistler mode waves that propagates parallel in the presence of an electric field with a ring distribution function in the magnetosphere of Saturn is studied. The method is formed by a kinetic method to ensure efficiency, consistency etc. at a radial distance of Rs. The expressions of dispersion relation, growth rate, and real frequency are derived to analyze the effects of plasma temperature anisotropy, relativistic factor, number density, AC frequency and energy density. Parametric analysis inferred that growth rate of Whistler waves increases with increasing value of temperature anisotropy and AC frequency, but the growth rate does not increase with number density ratio and relativistic factor. We find that a temperature anisotropy, T/T1.5, can account for linear temporal growth rate of Whistler mode waves, which provides a majority of the observed frequency integrated power. Higher frequency chorus emissions differ from lower frequency Whistler mode emissions and are sometimes associated with simultaneously observed low frequency electromagnetic ion cyclotron waves.